Hello, my name is Nico Geraldo, and this is Lab 4 Circuits. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, to use multimeters to measure the actual values of conventional current and potential differences in circuits, and to examine the behavior of ohmic resistors and capacitors. Some of the principles I used were the energy conservation, the loop and node rule, current conservation, and Ohm's law. A preview of the results from this lab were that the online model and the calculated values for voltage and current were the same. For the experiment details, the model I used were the online and ideal circuit models with different combinations of capacitors and resistors. The system was the circuit, while the surroundings were everything else. The assumptions I made were that resistance of the wires is negligible and the resistance of the ammeter is negligible. For the part 1, I predicted that the current in the first ammeter would be equal to the current in the second ammeter, or measured at the second ammeter, and that's just using the node rule. Model 1 was 2 batteries at 1.5 volts and 2 ammeters, 2 resistors, and one of them being 47 and the other being 100 ohms. I used the formula current is equal to voltage divided by resistance to get that the current should be 0.02 amps. The ammeter so for when the ammeter is replaced by the voltmeter, the voltage is 3 volts and the current is 0. So the voltage just stays the same, but the current in an open circuit is 0. So that's why it goes to 0. This graph shows the potential differences at the different sections of the circuit. And as you can see, when the graph is flat, the potential difference at those sections is 0. Another thing to note is that the total potential difference of this circuit is 0. When the ammeter is connected in parallel with the 100 ohm resistor, the current of the whole circuit increases because some of the current goes through the ammeter instead of going through the resistor. These are some calculated potential differences at required points. It's interestingly enough, the actual potential differences at the resistors are higher than the resistors are rated for. So for part 2, the model was using a 10 and then a 20 ohm bulb, a 9 volt battery, and 2 Faraday capacitor, or 0.2 Faraday capacitor. When the battery is still connected in the circuit, the capacitor is charging, and then the light dims until there is no light, and when there is no light, the current decreases to 0. Whenever you disconnect the battery and then reconnect the circuit without the battery, the bulb turns on and then dims again, and that's when the capacitor is discharging. So for the 10 ohm bulb, the capacitor takes 10 seconds to discharge, or around 10 seconds to discharge, and then for the 20 ohm bulb, it takes around 20 seconds to discharge. So continuing the part 2, the time-dependent model is a linearization of this equation. Well, this equation, and this is the linearized form. Instead of using a 10 or a 20 ohm bulb, we use a 30 ohm bulb, and the experimental RC slope was negative 0.1669. And then rearranging the equation down here, I can get that the time was 6 seconds, which is equal to the calculated RC, which is just resistance times capacitance. For sources of error, since the experiment was done on a simulation, the only error would come from human error, like measuring the discharge time or rounding too early. For the what if questions, the first one is asking about what would be different in real life with using a real ammeter. An ammeter in real life would have resistance, so the current would be lower in the real life scenario compared to the online scenario. And then the second what if question is asking about using a real battery to charge a capacitor with no resistor in the circuit. How quickly would our ideal model predict the capacitor to reach a full charge? So in a online model, the wire would have no resistance, so the capacitor would be quicker to charge. But in real life, since wires have resistance, the capacitor would take longer to charge.